All right, so the recording has started. So today we are going to discuss probability and distribution. So effectively, from now onwards, we will be discussing the applications of R. So so far we have discussed the various modules present in R, the basic syntax, understanding of the language R, and now we are moving on to application. So before we move on to real application, there is a little bit of a theory required on the probability front. So we will talk about that now. Okay. So first one is understanding the random process. Okay. Random process means anything could happen when you throw a coin. Anything could happen, but we don't know what particular outcome will happen. Second is the way we define the probability is there are several possible interpretations of probability. All of they say that it has to be between 0 and 1. Okay, so 1 means that it's 100% chance of getting that particular outcome. 0 means there is no possibility of getting an output. So what is the probability of getting a head on a coin which has head on both sides? If you have a coin which has head on both sides, so what is the probability of getting a head when you toss it? If there is a head on both sides of the coin, 1, right? And getting a tail on this, 0%. And had it been a fair coin where there is a head and tail, the probability of head or tail would be 50-50, as in 0.5. Okay. So whenever we talk about probability, we always talk about a value between 0 and 1, both inclusive. Now, there is a little bit of a difference in a gambler psychology or frequentist interpretation. You remember those movies where you watch a gambler and he says that, okay, he keeps on bidding all the time, believing that since he has been losing, this time he will win, right? Similarly, if you are tossing a coin and you tossed a coin and it came as head, the frequentist will believe that next one will be tail. Okay. Now, I'll show you a few more examples of frequentist interpretation of a probability. You will find yourself that you are one of the frequentists actually. Okay. So, but Bayesian interpretation is that probability as a subjective degree of belief. Okay. It's a subjective degree of belief that I believe that when I toss a coin, there are 50% chance that head will occur or the tail will occur. Okay. And based on this phenomena is the whole probability defined. Okay. What is the probability of getting 1 on a dice is 1/6 and so on. Okay. So now let's have a look at it. So question to all of you is that there is a village and there has been a tradition there that people keep on producing children till they get a boy. If they get a girl, they try for another kid. And then if they don't get if they get a girl, they try for another kid. If they get a boy, they stop. Now question is, imagine that this tradition has been going in that village for maybe 10,000 years. Okay, so what will be the ratio of male to female? You understood the question? In this village, there is a tradition that people try to have, people produce children only if they didn't have the boy. For the first time, they get the boy, they stop having children afterwards. If they get a girl, then they try for another. And if they get again the girl, they try for another. So the question is, what will be the ratio of male to female? What does your gut feel say? Hmm. Hmm. Do a computation. If there are, say, 100 people, okay, or let's just take with one person. What would happen? Ratio of boys will be more than girls. Okay. Okay. Let me ask you this. There is a room. There is a room. There are some n number of people. I give all of them one coin, and ask them to coin a coin. Toss a coin. Ask them all of them to coin. Toss a coin. No matter how many times. I don't ask them how many times. And at the end of it, how many will be heads and how many will be tails? Everybody is free to toss the coin as many times as possible. It's up to the individual psychology. Equal. Yeah. So you tell me what will be. Let's say I ask you that toss a coin 50 times. So what is the probability of getting head? How many heads on an average would be there? Their coin. Or say I ask you to toss a coin 1,000 times. So what will be the ratio of total heads and tails? Right? When the probability of head or tail is equal, so there will be equal number of heads and equal number of tails in a big enough sample size. Okay? Similarly, instead of you, if there is one more person who is tossing the coin for 50 times, other one is only tossing for 10 times, other one has another algorithm of tossing. At the end of it, total number of heads or tails will be equal. Similarly, in this village, no matter what strategy they have to have children, they will always be equal number of male and female. So, no matter what they do, okay, no matter what they do, they will always have there's an equal chance of a girl or a boy. I'll show you this. So let's say there is a person who had a boy. Now can I'll try to draw this. I'll try to draw this. And so let's think about it. What would happen? Okay? Let's say there was a person. The chances of having a boy and girl is equal, right? So this is equal as in 0.5, and so this is a girl, this is a boy, right? And here it's 0.5 and it's 0.5. Okay. Now after the boy is born, they will stop. Correct? But if the girl is born, again the chances of after this, the chances of after this, the girl is born, the chances of having a boy or a girl is equal, right? Equal. So no matter what you do, the total number of children will be equal. Okay. Basically, what I'm trying to say is, no matter what you do, you have no control over Mother Nature. No matter what you do, you have no control over Mother Nature, and hence there will be always equal number of children. Make sense? No? Still not able to digest the fact?
Yeah.
Okay.
So, for example, if a person 10% are there,
10% are there, let's say.
uh, first time itself baby boy.
First time itself, baby boy, all 10.
Yeah. So,
All 10, first time itself,
baby boy.
baby boy. So, what will they? They will stop.
Stop.
So, there will be a ratio of 10:1. 1. Correct?
Yeah.
But the truth is, you see, there is an equal probability, right? So, let's say there are 5 boys and 5 girls.
Okay.
Okay? Now, these people who are having 5 girls, they will try again, right? So, these people, out of these 5 people, again, 2.5 boys probability and 2.5 girls. Correct? So, if you notice that 5 and 5 equal number of boys and girls, and equal number here. So, at the end of the process, it's 7.5 each. And the girls is so 1.25 and 1.25. Okay? These many boys, these many girls. Now, at any stage, if you sum up, okay?
When we talk at this time,
Right,
probability.
correct. Similarly, here, how many boys are there? 5 plus 2.5 plus 1.5
Okay.
is 8.75. Both are 8.75. No matter what you do, you are going to have equal number of boys and girls. So you cannot blame this tradition for unequal number of boys and girls. Or for that matter, unless until they are killing the kids, unless until they are making it unfair. Okay? Unless they're trying to detect the gender of the baby and going for abortion or something else. Until then, everything is okay. All right? As long as the coin is fair, how many times you toss a coin will always result in equal number of outcomes. So, next time if you see on a new channel and somebody is blaming this psychology for unequal number of male and female kids, you will realize that that's not true. Correct? So this was important to understand that the probabilistic outcome, we need to always think about whether the probabilistic outcome are fair or unfair. Is their probability equal or not equal? Okay. We will use few terms such as random variable, a variable whose value is unknown, or a function that assigns value to each of experiment's outcome can be of multiple types depending upon the type of the quantity measured. So a random variable is another variable. Its value can be an outcome of some other variables. It can be a random outcome. Probability distribution is what are the chances of various outcomes. The distribution. The distribution as in a class, you take the marks of all the people and plot them on a x-axis. On x-axis, you will see some time or some value. On y-axis, you will see the density, meaning how many kids got 10 marks out of 100, how many kids got 20 marks out of 100, how many kids got 50 marks out of 100, and so on. Okay. right? Now, one of the most popular probability distribution is normal, or it's called Gaussian or the bell curve. So it was observed by lots of people that most of the behavior in the nature is in the world nature is normal distribution. In your class, if there are candidates, if there are students, and you try to note down their marks, you will find out that in the middle, towards the middle of marks, towards 50%, there will be maximum number of students. Okay. While towards lower side, say candidates who are having only 1 marks, 2 marks, or 3 marks, 10 marks will be on the lower side. Similarly, candidates having 95% marks. So always on the y-axis is the count of users. Okay. Always on the y-axis is the count of users. So on this one, you can clearly see that there are maximum number of candidates during the middle ranges. So in another word, on the upper limit or lower limit, there are very small number of candidates, while in the average range, there are maximum number of candidates. Right? Let's try to draw something here. Let's try to draw something here. The chance of getting a particular number is what we have drawn here. Okay, or in the example what we have taken is chance of getting a 50% mark is highest, while chance of getting 90% marks or 10% marks in a class is lower than what we have in 50%. Okay, so on the y-axis either is chance or it's the density, or we call the other thing is total number of people having that particular value. Okay. Now let's try to see whether when we throw the dice, we take two die, take two die and throw them. Okay. Once you throw the two dice, what is the probability of various values? Okay. So let's say we take the case of getting an outcome of 2. Getting an outcome of 2 is possible only in the case where getting an outcome of 1 is not possible using 2 dice, right? Because there is no such thing called zero phase. Because 1 you will get only if 1 is 0, other is 1. 2 will only get when both the dice say 1 and 1. There is no other possibility. And how many total number of possibilities are there? So what is the probability of getting 2? What are the total number of outcomes? What are the total number of outcomes? First phase can show up to 1 from 1 to 6, right? And the second phase can also show up to 6. So total number of outcomes are 36, correct?
Yeah.
Total number of possible outcomes are 36. First one 1, second one 1, first one 1, second one 2, first one, and so on, right? So while first one varies from 1 to 6, and second one can also vary from 1 to 6. Now in this diagram, as you can see here, the distribution is normal in the sense that if you go from left to right, the probability of 2 is there is only one case where you can get 2, which is both the dice, so 1 and 1. That means the probability of this is 1 by 36. We plot this chart here. Okay. Now let's take the case of 3. What are the possibilities? And here there are 2 dice. One we have colored black and other is white. So the probability of getting 3 is there are only 2 cases when you can get 3. When first phase shows 1, second shows 2. Second case is when first one shows 2 and second one shows 1, and that is there are total 2 outcomes. Therefore, it's 2 by 36. Now, in case of a 4, there are 3 chances. One is both the dice show 2 and 2. Second is one shows 1 and second shows 2. And the first one shows 2 and second one shows 1. And this is what it is. So 3 by 36. Okay. Now, the chances of getting a 5 is how much? Chances of getting a 5 is 1 and 4, 2 and 3, and 3 and 2, and 4 and 1. Now, the chances of getting 7 is probably highest. Chances of getting 7 is 1 and 6, 1 and 6, 2 and 5, and 3 and 4, and 4 and 3, and so on. And chances of getting 13 is how much? 0, right? Because that's not possible. So, and similarly, if you draw the graph, you will find that it has made something like a bell. Okay? So the chances of getting a number like 7 is highest, while the chance of getting 12 and 2 is lowest. Right? So almost everything forms a bell curve. Okay? Let us say that we are picking random 10,000 numbers. Random 10,000 numbers. Okay? So do you think will there be any possibility? So if we pick up random numbers, random 10,000 numbers, and we try to distribute, we try to count how many times 500 has occurred and how many times 300 has occurred, will there be a distribution like normal curve? Good. All right. Now, a few more things about, since normal distribution is like universal. It's a universal fact that most of the distributions in nature are normal in behavior, meaning they form a bell shape. To the extreme are lowest in chances, while the middle one is generally quite possible. All right. Now, there are very interesting things which are coming up with normal distribution. We'll do a lot of things. Okay. So there are many kinds of graphs, and the normal distribution is unimodal and symmetric, meaning it has got one peak. Unimodal means uni means one and modal means one peak. Okay. And symmetric means it's symmetric on both sides. Symmetric on left and right. If you cut it by a vertical line from the middle and fold it, both the areas will overlap. Or if it's a mirror over the vertical line. Yeah, it's vertically symmetric. It's not horizontally symmetric. Only vertical. Only circle is horizontally symmetric. Okay. And interestingly, the whole graph can be drawn with 2 variables. You only require 2 characteristics to draw various kinds of normal distribution. First thing you require is average, and second thing you require is standard deviation. Given these 2, so you will find in nature there are hundreds of kinds of values, okay, hundreds of kinds of graphs, that you can draw all of those graphs by these 2 variables. Okay, so for a population, if you know the mean and you know the standard deviation, you can draw their graph. Okay, and how is it done? I will show you. So basically, people found out that almost every graph follows this equation. This is the most interesting part about normal distribution. As long as we said in a very generic manner that this is a normal curve, it did not sound great. But when people said that I am giving you an equation which will represent all distributions of the globe, so most of the graphs follow very closely this equation. Most of the graphs follow this equation closely, not exactly like this. So what does this graph mean is that this function depends on average and standard deviation. Okay, so if you in a class, if you find out if there is a sufficiently large amount of data, you have say 100 points, and you find out their mean deviation and average, then you can quickly predict what will be the marks of how many people will be there in this marks range because of this. Okay, and this graph is also given to you when calculators were not there, when computers were not there. This graph was given as a table for various values of mu and sigma. Fx values were provided. For various values of mu and sigma, the values of fx given x are provided to you. All right.
How we can develop the standard deviation?
Standard deviation, I'll tell you. So before I move forward, let me define what is standard deviation. Standard deviation means x minus x average, and you square it and then square root it. Okay. Actually, that slide has, I think, moved a bit. Yeah. What is standard deviation? The last slide for standard deviation. Standard deviation is computed as standard deviation equal to square root of x minus average. Okay. And we say sum of okay. Actually, this has been moved and I don't like it. I think a better thing to do would be take these values, move it. Okay, I think I'll just shift a few things. Yeah, good. All right. Now, before I move on to the normal distribution, when we plot the distributions, in general, if you try to plot various kinds of graph, okay, as in you take the total number of values for any value, and so graph could be like left skewed, meaning that on the left hand side values are really high, value. There are so many values on the. I'm sorry, there are so much data on the right hand side, and on the left hand side there's a big tail. If there's a big tail on the left hand side, we call it left skewed. Symmetric means it's symmetric on both the ends. Right skewed means there is a long tail on the right hand side. Okay. Unimodal means there are different other kinds of graphs where unimodal means there is only one point, there is a maxima occurring, while bimodal means there are 2 points on which the maxima is occurring, while uniform is that there is no maxima or minima. It's almost like a flat graph. For all values, the distribution is equal. Now, multimodal is there are many kind of peaks. Now, let's say, now what does it mean? So, one graph is there where there is single peak, we call it normal. And there are another graph where we have drawn the ages of people. Okay. So, what we have done is on x-axis, we have the distribution of age starting from 0, maybe 2 to some value. Okay. And on y-axis, total number of candidates. If you do this for all the candidates in the college, okay, so there will be one set of people, okay, who will be teachers, and there will be one set of people who are kids. Meaning, there will be 2 peaks, one for adults and other is for nursery kids, because there will be a gap between the two. For adults like 15 years old, there will be no kids around, correct? Because it's a nursery school. All right. Yes, this one is height, and this one is the age of people. Sorry, this one is a height. This one is a height on the x-axis, and y-axis is total number of candidates. Always remember, in a Bannister curve or whenever we are drawing distributions, on y-axis it's the total, it's the aggregation, either in terms of probability or in terms of. So there's always accumulation happens on the y-axis in any graph. And trust me, this is something which everyone forgets. Height. So x-axis is height and y-axis is total number of candidates. So there will be no candidate on the height of an adult because it's a nursery school. So if there is no teenager, basically, that's what it shows. This is distribution graph. Okay. All right. And if you take things like very random numbers, say last 3 digits of SSN number or last 3 digits of phone number, the chances of getting 9, 8, 7, 1, 2, 3 will be equal, right? No matter what. In those cases, the graph will be fairly flat. But if you try to see the total number of people at various ages, then graph might be like this. There could be many kinds of graphs. So the left skewed says that on the extreme right, there are maximum number of people. On the extreme left, there are minimum number of people. Okay? Matrix says on the average value, on the median or the mean value, we have maximum number of people. Right skewed says the minimum for minimum value, there is a maximum number of candidates. Now the same thing if we do a box plot. Remember our box plot last time? Box plot basically draws the 50% candidates. Okay? It draws the total, the box containing 50% of the candidates. Okay? What does it mean? So on the left hand side, we'll have 25% here. and this will be another 25%. This will be the 50%. Okay. So the box will look like this one. It will has two, and the middle line is the mean. Middle line is the mean. Left border means the point where 25% ended, and the right border means the point where 75% ended. So middle 25%, middle 50% is what the box represents. In the box plot, that's how we represent the data. And so the graph which is left skewed, the box model of that will look like this one. First, the box will be towards the right hand side of the graph. Second, the mean value will not cut the box in equal way. Okay, the left hand side of the box will be bigger as compared to the right hand side in case of left skewed. In case of right skewed, the box will be towards the right. There'll be a bigger tail on the right hand side, and the box, the right hand portion of the box will be bigger because it will require more number of elements to make 25% here, 25% here, right?
Yes.
All right. Now, there are many kinds of graphs which are handled. There are many kinds of distributions that are handled, and every distribution has many kind of values. Is not too useful here. I'll just move it to the right place. All right. Now that covers the skewness. Skewness, as in whether uh, whether there are so many people, and okay. All right. So like for example, wealth. Okay. Like for example, wealth. The the total number of people who hold the wealth are very small. Maximum number of wealth, that is, so if you order people in the rich to poor area, okay, if on x-axis we put we sort the data on x-axis, we sort the data based on how rich are people, and on y-axis we put their wealth. The graph will be like this. The richest have the wealth which is far higher than the poorest, so it's more like a tail. It's more like a big tail. Okay. All right. Now, when we talk about any data, we talk about a central tendency. The one, how do we say that this is the middle point? Okay, this is the middle point. This is how will, on what basis can we say? One is your mean, right? We can compute the mean, take the average of all the values. Second could be the median. Third could be the most frequent value out of all the numbers. And fourth, so these are the three ways of measuring the main value. The central tendency, when you have a huge data and you want to find out the central tendency, it could be either based on mean, which is average. Mean is what? We take all the value, sum them up, divide them by their total number, And then median is take all the numbers, order them, and find out the n by 2th number. Okay? So that is our measure of central tendency. Okay? Let's have a look at an example. So you can have a look at example. So the numbers we have right now is 75, 69, 88, 93, 95, 54, 87, 88, 27. The mean of these values is nothing but sum them up, divide them by the count, which comes out to be 75.11. Okay, Bobby? Now the mode of these numbers is how much? Mode is most frequent number. Most frequent number is 88. But same count, just different. There's no. Okay. So okay, the third measure of the central tendency is computing the median. Okay. So mean and median have a tie, meaning which one should we use? Okay. So if you have to, Bobby, if you have to measure the central tendency, that a number which represents the central tendency of the whole lot of people, meaning the mean behavior, the average behavior. Which value will you choose? Will you choose mean, mode, or the median? Median. If your kid comes from home to school and you want to find out whether my kid is better than average or below the average, what is it that you will ask? Mean, mode, or median? Good. You will ask for the mean only. Good. Now, there's a reason why median exists, and there's a reason why median is. So generally, in statistics, median is considered a little better, and the reason is, okay. So this is just a graph showing income per person and life expectancy of various things. You can compute the central tendency of these. All right. Central tendency again, when you draw a graph which has got kind of a unimodal, but the left is skewed. This is called left is skewed. This is called right is skewed. Right is skewed means tail towards right. Left is skewed means tail towards left. Now, the central tendency of this one is median and mean. The mean lies here and median lies here. The mean lies here, median lies here. These are the same graph. These are the same graph. Now here, the mean lies here, median lies here, mean lies here. Now what you can see here is the important part. The median is very closer to the peak. Median is far closer to the peak than our average, because the tail is really, really big. Okay? So if you have to go near the peak in a graph which is either right is skewed or left is skewed, then you will go for median, because median represents the peak. Make sense to you? No? Right. Median is, see, if there are even numbers, so there are n even numbers, or let's say n odd numbers, you just order them, pick up the middle one. Right. No, it can be decimal number, right? It can be decimal number. Imagine this. Now there are odd even numbers. Even numbers case, in even numbers case, there will be two middles. Average can be decimal number. Make sense? Now, the way we do is, now you will understand why it's about median actually. So you can see that first median is very close to the center point. And interestingly, in the normal distribution, this is called normal distribution, where the single peak is there and it's symmetric on both sides. It's not left or right skewed. In this case, mean and median mean exactly same thing. Okay. So this slide has got missing. Okay. Now, my question to you is that suddenly there is a huge number, really huge number. So you had marks from 1 to 3, and say everybody in the class is getting marks from 1 to 90. And then there's this particular kid who got 99. Will this 99 marks impact the median or the mean? Right. So if you see median, the way we compute, we take the n numbers, we pick up the middle value. Middle value will not shift. This new number will just get inserted on extreme right. Will just shift by maybe one number. But this bigger number actually impacts our whole mean. You get the point? So say there is a room in which there are average people sitting. Okay? These are 10 people. Right? And their median is, their wealth is, say their average salary is 20,000 rupees. Now there is one person comes from the city, sits in the room, okay, and his salary is 1 lakh. Suddenly the total sum will be increased by 1 lakh divided by 11 people.
So when you are generalizing things, median is the
Yes. So when you do not want your central tendency to shift because of the outliers, you take the median. Okay? And the other situations are the skewness. When there are when the most popular skewness you will find as of today is the total wealth held by the richest people in the world. The total wealth held, actually the 5% of the people in the world hold 95% of the wealth. Okay, if you do not want these kind of outliers impact your average, then you generally take a median as the statistics.
It will come where the highest benefit.
Right.
Income may shift towards the wealthier side
Right.
rather than the remaining 90%.
Right. Right.
It's not the correct calculation.
Right. In that case, yes. So if you want to look at your central tendency in the way that it has to be always average, then mean will always make sense. But in cases where you do not want your central tendency to get impacted by a single outlier, a single outlier comes maybe by mistake in the form we filled 2 more zeros. Okay. Because of those kind of erroneous results, erroneous numbers, if you don't want your central tendency to get impacted, you consider median. And that's why median is considered as a stable way of measuring the central tendency. Stable because it doesn't suddenly move. All right? Now we compute something called standard deviation or variance. The variance and standard deviation, the only relation is variance is the square of the deviation. Variance and deviation, there are two things, right? One is deviation. These are two keywords. Okay. Now, what do these mean? These mean that standard deviation means that how much my values are deviating from my middle point. How much my values are deviating from the central tendency, which is average. So if while measuring the variance, we take the central tendency to be average, not the median. Okay, so the way we measure is The way we measure variance is S square, which means standard deviation square. Okay, and there are two kinds of ways. These things should not confuse you at all. I'll try to explain these things. So there's something called population variance and there's something called sample variance. Okay, so the way we do is that when you have say a billion number, you'll take a sample of say 100 numbers. So if you compute the deviation of those sample numbers, we call them sample variance. If you compute the variance of the whole population, it's called population variance. Okay, the relation between the two will be the number with which you divide here. In sample, it will be sample size, and here, in case of population, it will be population. Now let's come back to the main point. All right. So, all right. So coming back here, so variance is measured as summation of square of the deviation of individual value. So there are these two cars. What we will do is how much. Sorry, not two cars. I will actually give you an example. So let's draw the life expectancy of people. Okay. So let's say there is a table which is showing you in each country, what is the life expectancy of people. Okay. Now the deviation from the average is how much? Okay. Deviation shows how spread out is our data. How much are they deviating from the central point? If all the people had same age, let's say all of the countries have equal life expectancy, then what will be the deviation? 0. Okay. And if one is varying really high and other is varying towards the lower side or the any side, the overall deviation is there, right? Really high. And the way we compute is first we find out the average, then subtract average from each value, square it, and then sum it all, divide by total number of population minus 1, and we get the variance. And the deviation is the square root of this. The deviation is the square root of this. All right? Now, when we are computing the variance, why did we have this square? Good. One is, then why didn't we just put a mod here? We could have just put a mod, right? Very good point. So yes, one reason is we square it so that whether a deviation is negative or positive, it's a deviation. It should be summed up. It should not cancel each other. Second is, then we could have used simply mod. Why are we squaring? Sridhar? Are there more people in the question? So, Mitesh, are you able to hear me? All right. The other reason is we want to exaggerate, we want to increase the impact of deviation. That's why we square it. So that the visible delta should be higher than normal values. After that. But if you see, each value will get squared and then summed up.
And if we take the square root will be lesser. So if you sum up the more, it will be much bigger than the one. See.
No. So I'll give you the example. So x1 plus x2, x square plus y square, the under root of x square plus y square is less than x plus y the whole square. X plus y whole square is greater than x square plus y square.
Here we are taking.
So, okay, so what we mean to say here is the mod of the difference is the delta
Because I'm the root of the
square root of the,
whatever you have done.
okay. So we have delta 1 plus delta 2. If delta 1 plus delta 2, yeah. So, so overall value will be lesser than delta 1 plus delta 2 will be greater than delta 1 square plus delta 2 square under root, right? Okay, okay. So if we do a mod on each delta, yeah, you are right actually. Okay.
So the exaggeration, I don't know whether it's really same why you are taking this.
Okay, okay, here is the reason actually. Okay, so imagine this, the deviation is, one number is 3, other number is 1. Okay, one number is 3, another number is 1. So the impact of the bigger deviation will be more in the outcome.
Yeah,
that is the reason.
I mean, it's kind of a, if the deviation is more, the impact should be more.
Impact should be more. Yeah, that's what I'm saying. So if we are saying there is one number 1, other is 100 deviation, so 100 should have a bigger impact than 1. That's the reason we do a square. All right, makes sense to you? Okay. But for now, the general understanding is we square in order to remove the negatives. Okay. Meaning, what did we want to say here is, in case there are 1000 values, all varying by 1, okay, and there is one value which is varying by 20. So this 20 should have a bigger impact than these 1000 values. Okay, that is the reason why we square it. Okay. Now, moreover, it's just more like a understanding. You could come up with saying, why not cube? Why not cube root? Why only the square? Or why not to the power 4? Right? So, all right. Now, which of the following cars has more diverse in composition? Which one is more diverse? Set 1 or set 2? Set 1, right? So first one has got a higher amount of diversity. Okay. While now in this one, okay. So if we were to compute the diversity, then our formula will not be valid. I'll show you why. Now let's say there is another. Now we give the values to cars, not only the colors. Now this set one containing 5 cars, and their values are 10, 20, 50, 40, 30, or their mileages are that much. Now this set 2 where there are mileages are varying from 10, 10, 10, 50, 50. Now which has got more, the set 1 or set 2, which one has more variance or more variable mileage? The most variety, the diversity is here, correct? Because the 10, 20, 30, 40, 50, but the variance is on this side because the 51 are on the extreme right. Okay, so the average value, if you compute the standard deviation, it will be higher for this, lower for that, because there the values are spread out. The values are spread out. Make sense? Okay, so set 2, if you try to plot the graph, that one will look like that. Around 30, the average value in both the sides is close to 30. Here, the values are spread out equally, while here, the values lie on extreme ends. Okay? All right. There is an idea called interquartile range, which is That's also the measure of the central tendencies. Okay, when we have to simplify our whole range in three numbers, if we have to just observe a range and give three numbers quickly to see how the data is varying, it will be IQR. It has got three things. Okay, IQR has got two values, the left and the right, and the delta between them. Okay, so what does it mean actually? 25% candidate on the left hand side, 25% candidate on the right hand side, and this middle length is called IQR. So let's look at it other way now. So we take all the candidates, draw them on their life expectancy on x-axis. On y-axis, we just put the candidates here. So the total number of candidates on the left hand side is this length represents total number of candidates. Okay, and this, so basically for the candidates who have got 50, there'll be 50. If there is one person whose life expectancy is 50, we'll just put one dot here, and for 51 we put one dot, 52 one dot, and so on up to 100. Now we count the values, that how many people are there. We start from here, we reach till the 25% population, we mark, then we measure another 50%, we mark, and remaining 25% will be here. Okay, so this mark between first 25 and 75% is what we call IQR. Okay, basically it's a middle 25% of the data. Okay, inside it. Yeah, this left is skewed. So this is 50% of the data. This is 50% of data. Okay. So generally we shrink most of the model into our IQR range. Okay. Yeah. Right. Central. So we basically give three numbers generally to represent our data. First is average. Second is Q1. This is called Q1. This is called Q3. And Q2 is basically in the middle of this somewhere. Okay. So we give out Q1, Q3, and average. And IQR is this data. Okay. Statistically, it's a important idea. Again, the robust statistics we have already talked about is median or IQR. IQR is 50% data, that those values where it contains, because IQR will not change. IQR is more like median. IQR will not change because of some random variable comes into play. Similarly, median doesn't change. Median doesn't get pushed out because one big value or one very small value has come in. So that's why the median and or IQR are considered robust statistics. They are not impacted by sudden random extreme. And non-robust means that these things will get pushed and will suddenly change if there is a new variable which is lying on extreme cases. So standard deviation mean are non-robust, and so that's how it is. Now the example is given here. So earlier there were 1, 2, 3, 4, 5, 6. The mean was 3.5, median was 3.5. We all were happy. Suddenly 6 is removed and 1000 is pushed. Median suddenly goes to 169, while median is still is 3.5. Okay, just that for having mean to be sensible, you should have good enough numbers, good enough range. All right. So we talked about something called a normal distribution. Let me talk about it again. So what people found, most of mathematicians, including Gauss, one of the father of mathematicians, is father of mathematics. A lot of theorems are by his name. So They found out that if you draw the population, the count on y-axis, the count on y-axis, and and the values on x-axis, in almost every case, the graph was like a bell shaped. Okay. And even in a very simple situation where we are computing the probability of particular number appearing on while we throw two dice. We have two dice here in the first diagram. One is black, other is white. The probability of getting a particular number is what we have drawn on y-axis. And on axis is the number. Say for 2, there's only one case, which is 1 and 1. For 3, the way you can get 3 is in two ways, where first die get 1 and second get 2, and second the second possibility is one dice get 2 and second one get 1. For getting 4, you should, when you throw a dice, you should get 1 on one and 3 on another. Then the other possibility is you get 2 on both, and 3 and 1 is the third possibility. So as you increase the number, the probability increases. The chances of getting 4 is 3 by 36. There are total how many ways when you throw two dice together, in how many ways it can fall? When you throw a dice, in what all possibilities are there? How many possibilities are there? 36, right? So basically, to get 2, you have only one possibility out of 36 possibilities. Therefore, the probability is 0.02, which is 1 by 36, and so on. If you draw it, you will find that the probability of the extremes is very low. Like probability of getting 1 is actually 0, and probability of getting 13 is actually 0, while the probability of getting 7 is highest. So what lots of mathematicians found out, that whenever we are doing a population statistics, the diagram that came out to be was a bell shape always. There were very few numbers existing, very few people existing on the extremes, and maximum people existing on the bell-shaped curve. Okay, in most of the natural phenomena, this is what was the truth. Okay, and it was such a truth when they did more research. It was such a truth that they came up with an equation which even represent the actual diagram. So this is the equation which generally represent the graph. Okay, and there are two main characteristics which impact the graph. One is mean, other is deviation. So given a deviation and mean, you can draw the graph. The whole graph is a function of two things. One is mean, other is deviation. So if you give me the mean, I can draw mean and deviation, I can draw the graph. All right. So normal distribution is unimodal and symmetric. And okay, so I don't need to describe standard deviation here. I've already done that. All right. So I mean, you will find out that many variables are nearly normal. Okay. In case of R provides you really good set of commands to compute the various distribution. So normal distribution or Gaussian distribution is just one distribution. There are other formulas also, Poisson distribution, that also looks like a bell curve. Okay, but this one is the most acceptable curve out of all the curves available. Okay, so there are four kind of for each kind of distribution, there are these many distributions which are supported by R. The one which we talk about is normal, okay, normal. And for each of the distribution, there are four kind of things that are provided. First is, given a value, give me the probability. On y-axis is the probability, right? Okay. Given a value on x, give me the probability, that is P naught. Okay. Given a probability, give me the value, that is Q naught. And then a D is density. Density means this is for particular range, and R for random variable generation. If you want to generate random variable which fall into normal distribution, you can use R norm. Okay. Now, what I was talking about, given these two values, you can generate all kinds of graph. Like for example, here, the mu is 0, means average is 0, and deviation is smaller. Now, deviation increased to 3, and mu became 19. So these are two graphs. All right. So given two values, you can actually plot this graph. The average and the standard deviation. If somebody gives me, I can quickly plot the graph. Now, again, if my mu here is 30, mu here is 30, and delta A, the deviation is 3, the graph is going to look like this. It will be looking like this. All right. We don't need peak value. We don't need peak value. We don't need anything else to plot the graph if we know that distribution is normal. Bobby, did I confuse you? So these are the two characteristics on the basis of which we can plot any graph. And that's the marvelous thing about this normal distribution. So this is the equation that represents a graph. And this equation is in terms of mu and delta. So given various, so we'll just take mu and sigma from you. Mu and sigma means standard deviation, and keep on feeding various values of x and generating various values of y, and we'll get a bell-shaped curve. Okay. So if your delta is lesser, the graph is going to be steeper. And if the delta is bigger, sorry, sigma is bigger, the graph is going to be less steeper, broader, and the mean value will decide where does it lie on the x-axis. Okay. Steepness or the broadness is governed by deviation. Okay. And where does it lie on the graph, meaning whether it should be plotted there or here, is governed by mean. Okay. The other rule about normal distribution is this rule of 68, 95, 99.7. It means that starting from sigma, there is a single deviation. If you go towards left-hand side, a single deviation on both the sides, it will actually cover 68% of the overall area of the graph. Okay, 60% of the area of the graph, meaning the probability that since the whole graph is considered like the whole area of the graph is 1, then the chances of 1 point to be between this range is going to be 68.68. Okay. The area of 2 deviations is 95%, and the moment you reach to 3 deviations from the central point, you are going to actually cover 99.7% of the area. So this one from here, okay, this one from here to here almost has the whole area, meaning beyond this line, there is on both the sides only 0.3% area is there. Okay. Now, let's say there is a college admissions officer who wants to determine which of the 2 applicants scored better on their standardized test with respect to the other test takers. Okay. There are 2 kinds of tests. One is SAT score, other is called ACT score. One student took SAT score, other student took ACT score. Okay. So Pam got SAT score, and other the ACT got the Jim got ACT score. It's like saying I appeared for GMAT and you are appearing for CAT. I want to compare my score against you. Okay. So what I asked is that can you tell me the mean of all the students who get SAT and the mean of all the students who got ACT? They told okay, the mean for SAT score is generally 1500 and the standard deviation is 300, meaning the overall deviation, the kind of mean deviation is 300 for SAT score, and ACT score it's 5. So which one do you think is a better candidate, Pam or Jim? On what basis do you say that? So Pam is how far from the mean? One deviation. Great. And ACT is how far from the mean? Sorry, Jim is how far from the mean? Right? So Pam who got the higher, right? Okay. So on the higher side, plus the Pam got plus how much? Plus 1 deviation, while Jim has got hardly 3/5 deviation away from the mean. So graphically, if you draw the same thing on the graph, you get these kind of things. Okay. All right. So Jim is not on that extreme side, and therefore the Pam is better because Pam is 1 standard deviation while Jim is 0.6. Okay. Therefore, Pam is better. And this score, the one we just computed, is called Z score. Okay. This is called Z score. And Z score means observation minus mean divided by standard deviation. Now if your kid was studying statistics and he comes home and tells you in a random subject that, hey, I got 50,000 score, what is it that you are going to ask him? A single number. A single number that can tell you quickly whether he is doing brilliant or doing bad. Maximum? What was the maximum in the class? Okay. So he says that the score was 55,000 maximum. Yeah. Then does it mean anything to you? Will you be happy? He says that I got 50,000 out of 55,000. Will you be happy? No, what if 50,000 out of 55,000 is on the lower side? What if everybody has got 58,000? Sorry, 54,000 out of 55,000. Yeah. See there? If your friend comes to you and says he has got 50,000, what is the other number you are going to ask him? Or your friend comes home and he says that I've done brilliant in my exam, and you have to ask only one number. Then what is that number you're going to ask him? Rank in the class? Okay. Let's say he got 3rd rank in the class. Is that good? What if there are only 4 candidates? So as Mitesh was telling last time, he would ask for in what percentile of candidate does he like. Okay. Now the Z score is the one which one should ask. What is your Z score? The way we computed Pam or Jim, irrespective of which exam they appeared for, if we know their Z score, we can say who is better.
One person sometimes said, okay, what does it mean? He said 1 or 2. How that?
1 is great, 2 is great, 3 is great, -1 is bad. So the one who has got, if he comes up and
If there is one, if there are 100 candidates, if it's one, there are 40 people who is better than him.
I'll be happy if he says that he's one standard deviation from it, then he's doing good.
No, see, even if 10 candidates, 1 standard deviation is just a 68%. So there will be another 4 candidates who is better than him.
Right.
At least 2 candidates to this side.
Yeah, but he's doing good. He's doing good. It doesn't mean that he's doing bad.
If he is telling 3, then I can accept. Okay, this candidate.
So let's take a marks and try to plot it, and you will understand 1 standard deviation means that 1 standard deviation means he lies somewhere here in the graph. Okay, this means 1 standard deviation. +1 means here, +2 means here, and if he says +3, he's just brilliant. Okay, so standard the one is Z score. This is called 1 Z score. Okay, is mean it has a direct correlation with percentile of the candidates. Okay, percentage of candidates can be quickly computed based on the Z score. Okay, now let me show you what does it mean. How do you find out? There is a function in R called P norm. P norm, if you tell P norm that I have got how many score? 1800 on mean is 1500 and standard deviation is 300. Okay, so it tells you that this person is in 84% candidates. Okay, sorry, the 0.84 is the total area that comes under this. Okay, 0.84%, meaning somewhere like here, and that is P norm. Okay, now for Jim, which is 24, 21, 5. So standard deviation is 5. Okay, so it's 0.74. The probability is this much. Probability of getting that much marks given that scenario. All right. Now, if somebody says that I have got, now here, the candidate who has got 2000 marks, okay, he is on the 0.95 in the graph, okay, to the extreme right. Okay, that's what I was talking about when I said P norm. All right. So Z score can be used to compute the percentile. Oh, sorry, yeah. Yeah, this is correct. So generally, why we are talking about Z-score in the traditional term, when we did not have these functions called pnorm to compute the probability, what we generally used to do is we used to have these tables in which there is a relation between Z-score, and the probability, the relationship between Z-score and probability. And given a Z-score, you could quickly compute the probability. Okay. Now, coming back to, so if you know a value here, given X value, if you want to compute this area, you can quickly compute using P0. Okay. If you have 2 as the value, the area that will come from this to this will be what returned by the P norm. Okay. P norm will return the full area. So for -1, this is the area that is returned by the P norm. 0.15 means 15% of the total area. Okay. So we will utilize this P norm quite often, and again and again this P norm will give us the actual the area of this graph. Okay. All right. So now again, same question. In Z-score, Pam earned 1800 on her SAT. What is the Pam's percentile score? Can you try to compute from your R?
So 1 means 100%.
Yeah.
It should be the perspective.
And we don't know the maximum marks.
No, there is a problem. I mean, asking this one. So, there may be marks of, 300 or something. And the mean lays somewhere in 60. So, if there are 10 candidates who got 250 to 300, everybody gets the same effect score only.
Come again? Yeah.
Okay. There is a exam.
Exam.
Yeah, just exam.
Okay.
So maybe selecting only 5 candidates.
Yes.
Okay. So the mean lies somewhere in 50.
Okay.
Okay. The maximum mark may be 300. But for the marks from 200 to 300, there may be 20 candidates who got that one. But with research formula, everybody's research score is 1 only. So how you rate?
So you are saying that there is a distribution of marks,
yeah,
out of 500 marks, right?
Out of 500.
Out of 500, mean is 50, which means almost everybody is around 50 marks.
Yeah. But these 20 candidates who got from 200 to 300.
And okay, 200 to 300 marks. Yeah, so they are outliers.
Yeah. So
no, if you see standard deviation, right? Standard deviation when you compute, right? 200 to 300, the standard deviation will be really higher. Okay, because you remember, because of these variants, we are doing square. So standard deviation is going to be really higher. Yes. Okay. Now, can you try to compute the percentile based on this information? So, Pam earned 1800 on her SAT, where in her class the mean was 1500 and standard deviation was 300. Yeah. Try to compute using R. You have R on that machine?
With the P-norm, is it? Into 100 will give, but I don't know whether there is a command for it.
Okay. So the command is something of this sort. So the way we compute it for -1, if mean is this, standard deviation is this, we get 0.58, which means 15% of the area of this graph. Okay. And this area, right? This area represents total number of students. So if I have got -1, I'm saying that I am into 15.8% of the students, the lower 15.8% of the students, or I am then 15.8% of student. I think that will be better way of saying. -1 in this graph is better than 15.8% of students.
because his marks is here, which means there are 15.8% candidates which are lying here, here, like this. Because area represents the population.
So the standard deviation in all these cases you are calculating from the mean, not from median, right?
Not median. We are not computing median right now. Median is a good, robust statistics, but still it's not used for standard deviation. So can you compute this? Yeah. So what we want to do is we want to find out from how many percentage of the candidates is our PAM better.
You are showing 84 or something.
Yeah, but I want to see if you can use PNOM. So the way I'm using PNOM, can you also use? What is the percentile? What does it mean by percentile? Can you tell me? Percentile is generally said like, this candidate is amongst top X candidate, top X percentage of candidates, right? So what does that mean? What does 84%?
Better than 84%.
Better than. So C is amongst how many percentage candidate? Remaining 1 minus that much. So yes, correct. So this is what you used. Okay. So if you say 1 minus that, that will be your percentile. Okay.
So what is 1800 here?
1800 is her marks.
Okay.
Mean is 1500. SD is standard deviation, and the answer is that C is better than 84% candidates. If you draw on the graph, it'll look like here. All this graph is covered. So C is here somewhere, and all right.
So can you get a graph here, sir?
Where? Yeah, you can draw a graph. I'll show you the graph how to draw that. Okay. Sounds good to you?
How to know use the PNOM or norm?
Yeah, you will see that. So now next is that we are told that we are told that in the SAT exam, same exam, where mean is generally 1500 and standard deviation is 300. In the same exam, we were told that my friend is amongst 10% candidates, meaning he's better than 0.9. Right? 90% of the candidate he's better than. So what is the lowest possible score he could have gotten? This is where we use QNOM. QNOM is inverse of PNOM. Okay, QNOM will give us the actual marks given that 0.9, because he's amongst top 10% candidate, which means he's lying this side and he's covering 0.9 graph. Okay, so that's where you use QNOM, and then it'll give you the actual value. Okay, so if somebody tells me that I got this much marks, okay, this much marks, and I am in that percentile, so I can quickly go and check the mean and standard deviation of that particular exam and tell him that you are lying to me.
But only few exams give this kind of detail, like CAT or something. But
No, these all standard exams have to give the standard. We can find out the standard deviation mean. SAT and these standard exams, they give the mean and standard deviation. Yeah. Okay. So people cannot bluff me on the statistics. Okay. If somebody has got any X marks, I know the history of the exam. I know that is standard deviation of that exam.
But that is not the mark distribution may not be that Maybe
So there
you
is a,
will find that you may not get the exact mark, right? It may be varying because it's not a, I mean, symmetrical distribution anyway.
I mean, it will be varying a little bit.
Yeah.
It will be varying a little bit. The standard deviation, the mean, might vary a little bit, but not too much. Okay. All right. If you want to plot the graph quickly to see if you want to make something like a plot of histogram, you can basically say things like, you can say x equals to, okay, x equals to 1 from 1000, and then y equals to r norm of 1000. Okay, r norm gives you the random distribution of normal values. Okay, so the resultant values of r norm will be in the form of, r norm basically gives you a random number which fall into the normal distribution. Okay, I'll show you what does it mean. So I'll show you this 1500, sorry, mean is let's say 10 and standard deviation is 10, and if I say hist of y, you can see that hist means compute the summary and plot it. So it has, r norm has given me numbers which are maximum towards the mean, and there is a standard deviation of 10, which means 60% of the area will be here, and that way.
So y is a kind of vector with the thousand value.
Correct. Y is a vector with some values. Okay. So 1000 means 1000, total number of 1000 values I'm expecting. You're correct, and then answer. Okay. Now on the same time, if I do things like give me
Why
a
you define x there?
okay, sample, random sample of 1000 values. Okay, and I say histogram of y, it comes like equal. Okay,
Sample means,
sample is any random value.
but how it should be? I mean, that's the way it's designed. Like it should be exactly equal number of distribution.
So yes, so real random numbers are equal distribution, perfect distribution. So if there is a real random number, like real sample of 1000 values, it means that there will be 80 numbers on 0, and on 200 it will be same everywhere. But if I say give me a random sample of normal curve, r norm will give me 1000 values which lie randomly inside this probability
So if
distribution.
I'm not giving mean and standard deviation, what is it?
What?
If I'm not giving mean or standard deviation, what is it?
Then it will not pass, right? Okay, it has done something. I don't know what it has done. It has assumed something. Okay, so what did it assume? Standard deviation of 1, I think. Standard deviation of 2. And also mean, I think if it doesn't provide mean, I think it assumed to be 0. Yeah, mean it assumes to be 0. And standard deviation, I think it assumes to be 1 or something. Yeah, it is, I think 1 only. But if you see the graph, this is looks like 68% probability. Okay, sounds good.
Yeah.
All right, so these are the ways to compute distribution. Now, let me ask you this. If you are given any distribution in the class, and let's say you asked a friend of yours, can you are telling me that in your class this is the mean, this is the average value. Can you just give me the distribution in your class, the marks distribution? Can you just download the data and give it to me? And quickly, if you plot a histogram, if it is not giving you a binomial, I mean a normal distribution, then you should be suspicious of the data. Okay, you should be suspicious because most likely he has just generated random numbers, and and the graph, if he has generated just any random numbers, so the graph will look flat like this. Okay, like this. The graph will not look like a histogram. Okay, so that's where the quality of hist function comes into. Whenever you are given a data by somebody, you just quickly see the histogram. Histogram is what? On y-axis, total number of values, meaning frequency of values. On x-axis, the actual values. So how many times did 10 has come in the result? Okay. So histogram should quickly give you a first statistical inference of the data. Okay. Now, before we move into statistical references, the first thing which is very, very important, today's session is actually very important to all of us, because today I will be covering the gist of the game, gist of why did we learn R, why did we learn any other number system. Okay, so why? Because we want to figure out, we want to statistically infer the values from the data, and this is the first step towards moving into data sciences. Okay, this is the first step towards moving into data sciences. Okay, now when we talk about large numbers, the big data per se, okay, the law of large numbers makes the most sense. Let me just silence my phone. Okay, law of large number means if you have sufficiently large numbers, they will tell the truth. Okay, the individual deviations will be overcome by the largeness of numbers. Okay, say for example, let me ask you this: there are two hospitals. One is reporting, one is reporting that the ratio to male and female child is male to female child is 80 to 80 to 20. One is saying, there is one hospital says that ratio to male to female is 80 to 20. 80% of the children which are being born are 80 and 20% are only female children. Or I think I should make a more sensible question. So yeah. So let's say there is a hospital one where boys to girls ratio, okay, male to female children ratio is 60 to 40. Hospital 2 has got, say this, the ratio as per hospital 2 is 51 to 49. Which hospital has maximum deliveries so far? Maximum childbirths so far. What can you say about the total number of childbirths that have happened in these hospitals? Hospital 1 or hospital 2? Just let's say that these hospitals are not lying. They are telling us the truth. They are both truthful hospitals. Okay? And they have given these numbers. Hospital 1 says that boys to girls ratio has been 60 to 40. The hospital 2 says the boys to girls ratio is 51 to 49. Which hospital do you think has had maximum number of childbirth so far? 2. And why do you think that? Right, right. So 2 seems to be telling the truth. 2 seems to be telling the truth, and that is only possible if these guys are not lying. They are giving us the actual numbers. That means the truth is generally near the large numbers, and that's what the whole law of large numbers says. And the only reason Why big data matters is because of this. When you have complex equations, this, that, so much of, so the truth is always told by the large numbers. All right?
Mitesh responded.
What?
Mitesh responded.
Oh, I didn't see. So he's responding. Correct. Correct. So hospital 2, because 51 and 49 are not divisible by number. So that does not. Okay. So let's say we had 59 and 41. Now, Mitesh? It has nothing to do with the divisible or non-divisible. The thing is, hospital 2 seems to be telling the truth. We know for sure, right? We know for sure that, or let's say we are talking about coin toss. Okay, there is hospital 1 and hospital 2, both are doing coin toss, and we are getting head and tail in those ratios. Okay, so I'm going to trust the hospital 2 more because hospital 2 seems to be closer to the reality. I will consider hospital 2 be doing the more coin tosses as compared to the hospital 1.
How can you say that? Like, depends on the countries also, right?
Hmm?
Depends on which country.
Which country? No, in all countries the ratio is very closer to 1. It's not that big a difference. 60 to 40 is such a big difference, right? 60 to 40 is very big difference.
Some Indian states have best ratio like 60 to 40.
Yeah, that one is horrible. I mean, that is another scenario. I mean, basically artificially impacting it. That's another scenario. But still, even in the states like uh, Haryana, where there is a worst ratio, the ratio is actually 52 to 48. It's not that big a difference. And this ratio is actually humongous difference. If you even think about 51 to 49, it's still horrible because we generally count it in terms of the child rate per thousand in 3 digits. Okay, not in 2 digits. All right. So yes, this is still huge. Now the other theorem other than law of large numbers. Law of large numbers says that numbers don't lie. Okay. If there is a deviation, humongous deviation by individual, that is generally covered by other people. Okay. Now central limit theorem says that given certain conditions, the mean of sufficiently large samples of independent variable will approximately be normally distributed. Okay. So the way we just did, what we did was we took numbers, we computed their histogram. The data that was randomly picked gave us a histogram which was not normal. But if you compute the average, how far are their average, how is their average on the plot, then you will always get a normal distribution. Okay, let me show you this example. Let's say that we have got how many? 3 plus 3, which is 1 million samples of the data, random samples. Okay, flatly random. If you do histogram on my main data, it is going to be flat. Now we convert that into 50 rows. We convert this into 50 samples. Okay, we pick up, we convert this into 50 samples, each containing, sorry, we convert it into 1,000 samples, each sample containing 1,000 values, and then we do the mean of every value, which means we'll have 1,000 values, and then we'll have mean of 1,000 values, and then if we compute the histogram, we are going to get a normal distribution. Okay, the mean of the values is always, mean of all the samples is always going to be a normal distribution. That's another. Okay, standard deviation means sum of, okay, root of sum of difference between. So okay, let me try to put it in plain English. Standard deviation means you first compute average of all the values. Now subtract that average from each value. Now square this difference, square the difference of each value, then sum it up, and then divide it by total number of values, and then do the square root of that value. This is called standard deviation.
So then it will be the sum of the squares of the variance.
Squares
Square
of the,
root of the sum of the squares of the variance.
right. Variance is square of standard deviation. So I don't want to put the variance that way. Okay, variance is a term which we defined earlier. So I don't want to put that way. Okay, so I think this particular you have missed a bit. Okay, you can see that this is if you square root this value, then that will be S is standard deviation, and we are computing S square. Mitesh, does it make sense to you now? So what we did was we computed the average, we subtracted average from each value, we squared that difference, and then we summed it, and then divided by total number of record less one, and then square rooted. Okay. All right. So should I show you this demo? You can also try by yourself parallelly. You take the sample you take the sample of 1 million values. So my main data, if you see, is an array containing 1 million values. Okay, and if you see my main data, and we say 10th value, it's a random number. Okay, 11th value, it's another random number. And if we say histogram on my main data, histogram is flat. Okay, now we take a smaller section of this my main data and compute mean of all those values. Okay, so to do that, let's convert it into a matrix of 1000 by 1000. So mat is basically 1000 by 1000 matrix. Now on each row, let's apply mean. Okay, so row wise is basically 1000 average values. Okay, and if you do the histogram of this mean of these samples, okay, this is going to be a normal distribution. So the magic of central limit theorem is if you compute the mean of subsections of a data and then you plot that, if you do the histogram, it is going to be normal distribution. Okay, meaning the samples would have the mean which follow the normal distribution. Samples mean the will be on the normal distribution, meaning the mean of the mean which is lying near to the center will have the maximum number of means, and otherwise. Okay, so what does, yes, it can be applied to your normal day-to-day data as well. How do I hide the count? How do I? Okay. Makes sense. Did you try to compute it? Do you want to try to compute this one? Try. If Mitesh, do you want to try? If you want to try, please go ahead. If you get stuck, I'll help you out. Hist does the histogram plotting, meaning the frequency against the actual number. How many times an actual number has occurred, that will be on y-axis, an actual number will be on the x-axis. So it shows that those samples, it basically shows that those samples whose mean is how much? 500,000 will be the maximum. So the maximum numbers, maximum samples whose average is the 500,000 are going to the maximum. You got it? All right. All right. So this is called central limit theorem. Is your RStudio working?
Yeah.
Do you want to try this out? If you get stuck, I'll help you out. This will basically make you far more comfortable in R, so that tomorrow, if you want to quickly compute and tomorrow you want to just observe the data, it will be not a mental block.
Actually, I'm using R in my system.
Okay. Is it working for you?
Yeah.
Great. Great. If you are able to do this, then you'll be very comfortable with doing other operations as well. So is this clear, the central limit theorem to you, Mitesh?
So you are creating a sample data. If you create a random data,
So yeah, so it says that
now it's a sample data means it should be a straight line, right? Even the mean should be come straight.
now if you try to do hist on this, the main data, it'll be the way you are saying.
Yeah, but how the mean?
Yeah. So now next is first we convert it into how many 1,000 samples of 1,000 records each. Each of those 1,000 samples we do the mean.
Okay.
Which means we'll have 1,000 means. Now we are computing those 1,000 means on this.
Yeah, but we should follow the real data, right? Real data mean should not be like this, right?
Oh, like this?
Huh?
This is like, it will be like this. That's what central limit theorem says. So it says central limit theorem says that no matter how your samples are, if your samples are truly random, mean will always be mean. Mean will be closer to the actual mean of the numbers. If your samples are truly random, then basically your mean of the sample, those samples whose mean is very small will be very few. Those samples whose mean is very high, there will be very few such samples. Most of the samples will have the mean closer to the actual mean. Did I make any sense? No. Okay.
No, I mean, something.
Yeah.
No, I couldn't understand because
Let's go
we
step
are
by.
plotting sample 1 to 1 like whatever it is. So the numbers are equally distributed between all these things.
Yes, that's correct. Try plotting, try doing hist on my main data.
And then it will be kind of square, right?
Square only, right? Yes. Now, next thing what we have done is we have computed mean of these numbers, average of these numbers, each sample's average. Now imagine each sample, let's say there are 1 million numbers, right? So, or let's just take 10 numbers for that matter. Just take 10 numbers. So 10 numbers are here. First sample will be first number, maybe 10 number, and so on, right? Or should I demonstrate to you this one? Can we check that the mean of main data here? Yes, you can try that. Or let's make the life little simpler. Okay, let's try with a data which is just very small. Say your 100 samples. Okay, so my main data is only 100 numbers. Okay, if you do histogram of my main data, then it's very flat. It's
So
very
then
flat.
I apply my,
Now if I compute if I take 10 samples out of it, okay, or I just fold it into 10 numbers, I just pick first 10 then second 10 and so on, because these numbers are anyway random. So if I fold it into, where is, yeah, into 10 numbers, okay, 10 numbers, so this matrix is going to have 10 numbers. Now these 10 numbers, if I compute average of these 10 numbers, what do you think the average is going to be? Will it be closer to 10 or closer to 100? The average. These are random samples out of 100 numbers.
so
The average of these 10 numbers is going to be closer to 100 or 50 or 10.
it's closest to 50 because
50.
they're random one.
Yeah. So this will be 50, 50, 50,
But the
50.
top one, it will be nearer to 10, right?
No, these are random. Had they been in sequence and we have taken first 10 then second 10, so if I have done this, then I could have been cheating you. Okay, if I had done this. Okay, all right. And now after computing average, now if I do average on this data, average on this data, and I have got row wise. So just a second, what did I do? My matrix is this. Yeah, I say column wise. Okay, I say column wise. Now you see that. Now see that first sample the mean was 5.5. Then it's increasing monotonically, right? So that's why the condition in central limit theorem is it has to be the mean. Yeah.
What was this one? Could you show the example? The row wise. What is that apply command will do?
Apply will take mean function, and for each row it will compute the mean.
Oh,
Any function we pass there, each row's data will be given to that function, and that function basically computes the value and generates a new data set. One means row. If you want to apply column wise, we can put 2 there. It will generate a vector of numbers which are mean of each row in our matrix.
then we plot the matron and matron.
We'll do the histogram. Histogram means computing the frequencies.
Then that's what I was confused. Let's see.
Okay,
So I did two data I created. One is sample,
perfect,
other is random.
correct.
So sample, the row wise histogram will give you the square. So it's correct. The other one will be, but your
Exactly.
example it was showing.
No, no, no.
that,
Yeah. That's what I was saying you. So if I,
that I got confused.
I'm sorry. Let me try to demonstrate you what you are saying. So if I plot this, you were right. The data will actually get like this.
Yeah, that's what I thought.
Meaning-
Because you saw sample. I saw sample.
Okay, okay. My bad. Yeah. So here again, if you, so this is clear, right?
Yeah, because you mentioned the top one is sample, right?
Yeah. This one is sample data.
Yeah.
And then after that, we are computing MAT, which is basically the,
Yeah, like
row
if
wise is the man.
Yeah, if you that diagram you won't get it.
Right. Now, if you do,
It's only for random.
if you see this, this is histogram of the mean.
It will be square. Rule.
Yeah.
No, you took random data or sample?
This is for you also try, right?
Yeah, I got square.
No, there's something wrong.
Histogram of-
Let me share your screen
Because
so that
I
Mitesh
took
can also
sample
see.
data as
Are you on the GoToMeeting?
No.
Okay.
See,
So
I did two things. My data I took sample.
Correct.
And my data one I took arm. So my data, that one comes.
So
with the-
yeah, this is okay. But after you have applied mean, can you try to plot row wise histogram of row wise? Histogram
Oh,
of
raw wise I didn't know very much. Maybe that maybe that is. Oh, okay, that was a.
Okay.
Why is that way for the sample also? Because it should be an even distribution, right?
No. If the numbers were truly random, one will be 10, other will be 50, other will be this, and other will be this, right? The mean of them will be closer to the middle.
No, I couldn't understand. Say, sample created data, okay, but how it look like doesn't matter.
So
to
sample
100, say.
sample will be random, right?
1 to 100.
Correct.
So you are dividing it into 10.
Yes.
Okay.
10 records I'm picking up.
Okay. So the average should be around 10 only.
Every record's average will be how much?
It will be 10 only. Right?
No. These are out of 100, right? These numbers are out of 100. So their average will be 50. Close to 50. I'll show you this.
Even for the.
So if you are picking up 10 random numbers out of 100 numbers, their average will be how much? 10 random numbers out of 100.
10 numbers out of 100. Yeah, around 50.
Around 50. That's what the CLT
But
says.
it's most probably, since it's a sample, it should normally be an equal distribution, right? It won't happen.
Equal distribution over the range.
Yeah.
Okay.
But here, okay.
Over. Am I confusing you?
No, okay. How this applies?
So this is theory wise it's clear, right? Whenever we are picking 10 numbers out of 100 numbers, 10 random numbers out of 100. So these 10 numbers can be from the beginning, can be from the end, and should be spread out properly. If you average these 10 numbers, the chances are their mean will be very closer to the center point. And that's what is normal distribution.
I made a mistake here. Let me try once.
So, using central limit theorem, you can quickly predict how well the data is randomized. If the data is not well randomized, you will not get a histogram. Or let me ask you this. Is this statement correct? Is this statement correct?
See, it's not histogram. So, only problem is that it's how you plot your histogram. That's the only thing.
Not really. Not really. If you
Hey, see, come here. That's what I could see. So, see,
This the range is 50,000.
So your overall mean is a half million. So most of the numbers are close to half million.
See,
This is zero. This is some other data. Raw H1.
the same only. That means I have taken a random value. Then it's giving this number.
No, both data is in random.
And the histogram. And in this case, yeah, that 40,000. So if you creating one histogram of, if you are really creating from the 1 to 1 lakh, no, 1 million, this is actually comes in a single histogram only. You are just showing this.
No, no. So the question here is the mean of a random number. So there are, let's say, 100 numbers. Let's just for simplification, there are 100 numbers. You pick up 10 random numbers. 10 random numbers. Pick up 10 random numbers. Now compute the mean of these 10 numbers. Will this mean not be equal to the 50? If you take 10 numbers out of 100, the chance, do you think there are higher chances of mean being equal to 50? Actually, that's what it holds you down. So it says that mean of samples, right? Mean of samples should be more numbers will be there, more means will be there equal to the actual mean.
Yeah, I understood.
Yeah.
I looked at the data in a different.
Yeah. It takes a little bit of time. The way the example is structured, I agree with that. It takes a little bit of it's not that obvious. All right. So are we on the same page now? So central limit theorem is clear, right? If you plot histogram of mean of all the random samples, it will always be basically the centroid of all the samples will be near the actual centers. Okay, the centers of all the samples will be near to the actual sample if your samples are truly random. Okay, now whenever we are taking samples, we our strategies are very prone to biases, and this central limit theorem helps us counter the various kinds of biases. And what are the various possible biases are? One is convenience sample, meaning those people who are nearby available here only. I say that that is my convenience sample. So let's say I'm doing a study. I'm doing a study on the purchasing behavior of people online in online, what is the purchasing behavior in general. And I went to the fire exit and I found some 50 people smoking over there. I went and asked them, what do you want to what kind of things do you purchase? So this way, because of the convenience, we induced a bias. Here, the people who are on the fire exit smoking, they will have it's a small sample. These are the people who are being paid by IBM, those who have good enough salary, and therefore there will be a bias. There will be a behavioral bias in the in the in the overall sample. Next is voluntary response. Now, this happens when you say that, okay, you want to understand what is the public opinion on, say, should West intervene in Syria. Okay, so chances are those people who will forcefully come to give their opinion, okay, they are the people who are being impacted the most. Okay, so there will be volunteers. Somebody would be forcefully a volunteer. Okay, you posted a newspaper article. The chances of attracting the volunteer will also induce a bias. What kind of volunteers are coming? Okay, now let me ask you that. So, and non-response, I'll talk about the other parts later. Non-response is that, okay, so the people who are responding, the main population may not be responding to your surveys. So sampling methods are complex, and basically whenever you do the statistics, you do the sampling methods, various kinds of sampling. One is normal, simple random sampling. If you are lucky, we will be able to do this. If we are having all data and we want to just pick up some random data, we just generally use simple random sampling. But the problem is that generally that's not the case, specifically when we are conducting study and collecting the data. We basically divide the data into homogeneous strata and randomly sample each strata. So we may say that it's Bangalore, it's Delhi, and so on, and we basically sample that way. Other is the cluster sample, rich, poor, this, that kind of sample we create. Okay, and and then we pick up few samples, few clusters out of the main. These are the various sampling technique. Other is experimental design. This you will use when you are designing a product where there is a A/B testing required. For example, so what is A/B testing? Quickly, so we take some subjects. Some of them are given injection. Some of them are not given real medicine, and we see the response time. So this is a very good statistics application. Now, the A/B testing is also very much valid in case of our normal computing. Okay, so generally the way we design experiment is control. We basically we call something called control and treatment. Control is the actual the way uh, people were doing their normal life, and treatment is the people who have been given the treatment and so on. Okay, so first of all, you basically compare the treatment of interest to a control group, then you randomly assign the medicines or treatment to various people, and then you collect the large enough sample or replicate the entire study, and then you block for the variable known or suspect to affect the outcome. We remove the situations which affect our overall design. Okay, now trust me, the placebo and placebo effect are very much popular, so you need to be very much cautious about placebo effect. What is placebo effect? Placebo effect says that there are circumstances where even if people are given the fake medicines, people have responded with a positive signs. This is placebo effect. For example, the placebo effect is a very much prevalent in case of the certain kind of medicines. Okay, so specifically related to the psychology medicines, placebo effect is very popular. Meaning, even if you gave somebody a fake treatment, they responded saying we got better. Okay, and you do the binding generally. You do not tell the patient whether you are on real medicine or you are on a fake medicine. Okay, next is you do the double blind is one technique where even the doctor does not know whether he is giving a placebo or whether he is giving the real medicine. Okay, so that's double blind. All right, so here you can see that there was a population. We wanted to understand whether whether they like the sans serif font or they like a serif font or sans serif font. Okay, so that is our confounding variable. What is it? The principle on which we want to. What is our overall objective? Now, random sampling is we pick up the random candidates and then we assign random candidates. Some go to serif, some go to sans serif, and that's kind of we do it. And this is very common technique when we do the A/B testing. Half of Amazon actually runs on A/B testing. Okay, all right. So you want to take a break now? We will go for lunch and then come back. So it's 12:42. When should we come back? Mitesh, Sridhar.
no problem. I need to leave by 3. That's
Okay.
all.
Okay. 1:45. That'll be okay. 1 hour break. All right. So back by 1:45.